Right then, ladies and gentlemen, welcome to the theatre. We're going to have a very, very good session today, and we're leading off with Michel and Christian, and we're going to be chatting about one of the critical parts of keeping your data centers resilient and keeping it going, the cooling. So what we're going to chat about is the new technologies, how AI has really, really ramped up the amount of cooling that your data centers need, and how new technologies are needed to be deployed in order to allow people like my daughter to make emojis out of me at night using very powerful computers in your data centers. So, without further ado, Michel, Christian, the floor is yours, guys.
Excellent. Thank you. So good afternoon, everyone. My name is Christian Senu, and I am the global leader for data centers at Carrier. And what that means is I have full responsibilities from the product roadmaps through our manufacturing, our strategy, and ultimately our partnerships with our customers. And I'm sharing the stage with Michel Grabon, who's our technical director for Europe. And if you could do a quick intro, Michel.
Yeah, thank you, Christian. So I'm not a professional speaker, so I'm sorry for this, but I had the chance to talk to you last year already. Maybe some people remember our speech from last year. So I will define myself as engineer. So I'm engineer since more than 30 years. And today I'm spending majority of my time helping our business, to develop some solutions and work on mainly on data center cooling and controls aspects.
Right. So we have a couple topics up there, and really is meant to be a little bit more of a dialogue, because as the shift to AI in data centers is required a couple of things. One, your thermal solution has to evolve to deal with the increased thermal densities, but also you have to make sure that we're continuing to be sustainable in the overall data center architecture, but ultimately what that cooling solution provides. So, again, the slides are really to support the conversation, and we're just illustrating with one of the chip manufacturers. There's two things that you see. As that thermal density continues to increase, but then also you can see the frequency of the innovation in the chip roadmap continues to also increase. So over the last few years, that thermal density has continued to increase, which has required the shift from air cooling and into liquid cooling. And introducing liquid into the data center and that technical cooling loop has really created an opportunity for us as a thermal solutions provider to really innovate and partner with our customers to really drive a comprehensive and end-to-end solution. Because when you think about a data center, similar to other buildings, the largest load after the IT load is dedicated to the cooling equipment. So the best you can do to drive the efficiency and performance there, you can ultimately drive a broader system efficiency. So when you think about the opportunities we have ahead of us, is providing the liquid cooling solution. It's also solving other problems that our customers face as they look to build at scale and at pace. And that's introducing modularity. And Michel's going to go into some of the details around our end-to-end solution and how modularity can help with speed, which ultimately drives costs and quality into the process. And then the last thing is, how do you take the history of Carrier, the innovation, and the physics-based modeling that we have developed in our products and our technologies with AI to get the best of both? You're leveraging high advanced technology at the same time as the fundamentals in engineering development, and you're bringing those together to a really innovative and integrated solution. So Michel, if you could take us into about liquid cooling.
It's a subject, maybe some people are joking about me that I have actually the passion for engineering and in particular thermodynamics, so it's sometimes it's not obvious. But maybe I will start with some basic physics. I think that usually people are using some words like liquid cooled, air cooled, etc. So I will just very quickly try to share with you what I'm thinking about why we are doing this and how we are doing this and what are the impact, without without showing you complicated formulas or demonstration. But we need just to think about one very, very basic thermodynamic assumption, or I would say physics, is that basically you cannot destroy energy. You cannot destroy heating. You cannot destroy energy. You can only displace. You can move it. Okay, so this is how it works. So that if we were, in situation to by some magic to destroy heat of the chip of CPU, GPU, we would do this. But there is no way of doing this. So because GPU and CPU are consuming electricity, a lot of electricity, that you have shown. Currently, we are talking about hundreds of watts, maybe kilowatt, in very, very small space. So there's two aspects which are important. One is to take this heat out of the chip in efficient way to keep temperature of silicon low enough that it's not destroyed. So this is heat transfer coefficient. And from this reason, liquid is better than air. That's why we are talking liquid cool. Liquid cool is not because we like liquid cooled. There is no other way removing the heat from CPU, GPU, chips, or whatever hot surface you have than having high heat transfer coefficient. And it happens that liquid has higher heat transfer coefficient than the air. So we have to use liquid to cool high density chips. We don't really like liquid because liquid is you have to difficult to handle. You need to bring this inside. It's much easier to make the links, thermal links with air. But because of the density, the only way of removing the heat and maintain silicon and a decent temperature is to use liquid. Okay, so we have to have liquid. Liquid has some advantages also because it's heavy, and you all remember. I promise not to use formula, but I will tell you MCP delta T, you probably remember from school. So the liquid has much higher M, the mass, liquid is 1,000 when gas is 1, and CP is 4 when for air is 1. So basically, as I said, you need to not only to maintain the temperature of the chip, you need to move this heat outside of data center, and eventually, this is what I was trying to show in this slide, to throw it away to the air or to maybe district heating or maybe to the sea. And I was trying to show, in this picture, it's probably too busy, that, this heat is going from GPU first maybe to a rack, and from rack to CRA, from CRA to chiller, and from chiller to outside in the traditional air-cooled data center. In liquid cool, it's a little bit different. So we are going from GPU, CPU to the rack, from rack to CDU. So all those links, and from CDU to the chiller. So from all those links are based on liquid. An advantage is actually that when you are pumping this liquid with property of liquid, it's actually cost less energy to carry heat using liquid than using air. And you see this value, it's about probably generally speaking, if you were talking that you need to have a lot of energy to remove this heat. Right. So in air cooled maybe 15 to 20, 23%, and liquid cool it's less, 10 to 18. So this high density data center, high loads, also forces us to be more efficient if we want to be good, for environment and for operating capex. So this is advantage of liquid. So I recall this. One is to maintain temperature in the correct level because of the heat transfer, but also allow cheaper or lower energy content in transferring this heat eventually from our chip outside.
Right. So let's share a little bit about how our solution can provide that in terms of the suite of products within our Quantum Leap offering.
Yeah. So I show in the previous slide, there is not only chiller or there is not only CDU or airside. There is a lot of circles or circulating fluids and a lot of components. And basically what we as Carrier doing since 120 years already, because we are in the very beginning of this energy transferring business, which happens to be cooling, heating, or data center or air conditioning. And basically, it's like a human body. You have several elements. You have chiller, you have air handlers, you have CDUs, you have pumps, you have controls, and basically you can silos them, slice in different elements, and what I call losing synergies between elements. You will not optimize overall system, which this optimization depends of ambient condition and loads, etc. Or you can have comprehensive a synergistic approach, which Carrier is doing,
right.
and providing all thermal elements of the system in a such way that we are extracting from the given assets maximum of value, so lower possible efficiency. And this is what quantum leap is. This leap comes from the holistic approach and vision of the architecture of building the elements, but also operating those elements as a whole.
Right. So it's been, pretty amazing as we've launched this Quantum Leap offering to really take core strengths within our portfolio and integrating them in a way that solves problems and challenges our customers face in a way that's really driven better efficiency, reliability, and performance. Because if you take the individual components of themselves, when you bring them together and orchestrate, you find a way to actually drive better system efficiencies, which has been very helpful for our customers.
And if I may, Christian, one additional comment, I don't remember if you have slide talking about this.
Yep.
There is all, which I call maybe supply chain, but maybe we should say organization of build of data center, which is very important. So when with traditional lower density, lower capacity data center, it was acceptable to do, for instance, for each component, 1 week of commissioning for the chiller.
Right.
When you will have 100 or 200 chillers in the roof, you cannot afford to have 20 weeks or 100 weeks of commissioning. So it also this density and this scale oblige us, which are partners in data center, to rethink building process. So, we used to provide chillers, somebody else used to provide piping, some valving, some strainers, etc. And then somebody was checking, everything is okay, commissioning, looking on the leaks, etc. Today, when we have 200 megawatts, 500 megawatts, 800 megawatts, a number of chillers and elements becomes, huge. You need to be able to reduce commissioning time, installation time by the factor of 2 or 3.
Right.
And the only way of doing this is to integrating as much as possible functions and elements in the what I call chiller function and not chiller elements.
Right.
In a such way that it's already tested, pre-commissioned. I don't know if we can call this L3 or L4, but when it arrives on site, there is only 2 connection points, and all the leaks, all the other elements has been checked before.
Right. So pre-fabricating, pre-integrating within our facilities or partner facilities prior to going to job site has been absolutely a game changer. So let's just transition a little bit. When you think about sustainability, what are the ways that our solution can help drive that? And what are the things that are important? So yes, decarbonization is absolutely important. When we look at our supply chains, the embedded carbon within our products, and how we actually approach delivering the value. But then how do you make sure that as the data center is in operation, which, when you look at the large announcements around CapEx and the commitments of all the data center operators, sometimes it's hard to talk about the many years of operating the data center, and that's where the real impact ultimately comes in. So making sure that we have the ability to, one, measure, track, monitor, and then ultimately optimize the performance has been really the game changer for us to make sure that, one, we have the ability to model the solution before the data center is fully designed, fully implemented and commissioned, so you understand the expectations. But then 2, as you're operating, how do you make sure that you're continuing to optimize that and minimizing the impact? Also, we've done many projects, and Michel's going to spend a little bit of time on one around how are we making sure that at the data center system design level, we have the ability to reuse some of the heat rejected, or we have the most efficient system depending on the location, the use of free cooling, and the other different ways that you can minimize the impact that the data center construction and operation ultimately has on the environment. So Michel, if you can spend just a little bit on some of the different ways that we've done.
Just give maybe 2 or 3 examples.
Yeah.
Before going there, just one generic comment. We Carrier, and I have 37 years of experience with this company.
37 years old.
Yeah, we have a kind of green DNA. So I'm talking about, we are not just communicating about this, but if you think about product development processes, manufacturing processes, all process in our company. We were not waiting data center boom, 2, 3, 4, 5 years ago to have this culture embedded. So for instance, and you just mentioned about this, but I think it's important to just highlight this. For instance, our product development processes includes, circular economy, using reusable material. We are monitoring energy consumption by standard hour in factories, etc. So we have already embedded a lot of green elements in our data center, and very naturally, when we started to work in data center, I'm talking here 10 years ago, the first obvious elements for us, it was even before it became mandatory in Germany, in some other places, was to reuse heat from data center for instance, district heating. So you have here few examples which we did, and this is not like last year, it's 10, 15 years ago. You see here some example when we are converting, and you can see that water temperature in this time, 15 years ago, was much lower, so 20, 15, maybe lower temperature. And I don't remember exactly what is the amount of installation which we have, but we were doing transfer of energy and cooling of data center and transferring it to district heatings with long time. And we have developed, this is relatively original, we have developed a line of products, which are water-to-water heat pumps, which were dedicated to this specific function. So take relatively high ambient, high water temperature from one system, system A, which could be data center, 20 degrees, 30 degrees C, maybe even 40 degrees C, and transfer this to the usage, which can be district heating or some industrial processes at the level of 70, 75, 80, 85 degrees C.
That's right.
And those products are standard product coming from our factories. So it's not like, dedicated build to order for specific application. It's just specific chiller for this application. So we have those chillers and we are ready in the market, just to install them close to data center and transfer the heat to the district heating.
Yeah, no, and that's a great point because, being able to manufacture and execute your processes in a sustainable way and then ultimately partner with the designs in a sustainable data center design has really been a game changer. So going into the AI optimization piece, what are some of the trends and the things that are happening in terms of the power density, the sustainability, and the complexity increasing? That just creates the time for us to actually go beyond the traditional science and physics-based modeling and accelerating that one in the ability to monitor, the ability to model, and ultimately optimize, again, that total solution by bringing those two together, right? So you're not just taking an AI model that can learn, you're using the physics-based principles and the design and technology that we've iterated and evolved and improved over time and combining them together to really drive, really differentiated outcomes.
Yeah. So I don't want to make the bad jokes and say that we need AI to optimize the system and we are using cooling just to run AI to give just
the circle, man. Yeah.
No, so it's very little amount of this. But seriously, it's a very, very important subject, and people usually talking about this, and we have a couple of papers we wrote about this. In the complex system like data center, when you have a lot of assets, a lot of chillers, a lot of different elements, pumps, etc., and you have very variable load and very diverse operating condition, there is no one way of running the system. There is several ways of running the system. So I call this degrees of freedom. There is a lot of degrees of freedom to operate data center. In other words, imagine it's a little bit like with cars. You can have different style of driving. The same thing with data center. You can, for instance, if you have half load of data center, so you just need half of your cooling, but you have 100% of your chiller available, you can say, okay, I'm running all the chillers and 50% load,
right,
or half of the chiller and 100% load, or 66% of some whatever load. So there is an array of solutions. And there is between all those solutions, there is only one which will have the lowest input power, so the highest efficiency.
Right.
So all these elements of operational optimization is to be able, by virtue of you can call this digital twin, or you can call this physics-based modeling, basically recreate environment which looks and behaves like data center for the given operating condition, but in the computerized, space, and predict in this specific moment of time and the specific ambient temperature and load, what should be the number of chiller running, what should be the pump speed, what should be the temperature, and you see this in the right side, and whether force the system by intelligent controls to change the stage and go to the state which is optimum, or just propose to the operator and say, you guys, and you see this, if you, in the right side, if you, in this specific time, if you change your water flow, you may gain 5% of energy, in 5 minutes to come. So we're still working with data center operators to find, because I know how the people are risk averse, so we need to get a little bit of confidence. But generally speaking, it's our specialty to kind of do modeling, understanding the physics, have optimization layer, and AI can help us, in this. It's not doing everything. So I would say, from my personal perspective, it's 75% of physics, maybe 25% to make this AI, because we will learn as we do this optimization of what is the best solution. And by the way, Carrier has what we call a bound, so it's a part of the offering when we can exchange information between different experiences in different data center and learn, that we have already 5,000, operating points, and in this particular situation, it was proven by physics base that it's better to go this direction. So it's a quantum leap. It's a comprehensive vision of what we do with information, how we treat it, what is the system level elements, and how to help drive reduction of input power in data center.
Perfect. Well said. And really, when you just think about the AI driving larger thermal densities, driving more complex solutions, which requires Carrier, which is a company committed to sustainability, to one, operate and build effectively and sustainable, but supporting the development of sustainable architectures, but ultimately is bringing all of our products, solutions together in a way that optimizes throughout the life cycle of data center operations. So, that's the last of our message. We want to make sure that if you have an opportunity, please come by the booth and you can learn more about more specific solutions and other ways that we're solving problems with our customers. We are right on time to take a couple of questions if anyone does have some. Otherwise, please come by our booth and see us.
And maybe I just add one more comment.
Absolutely.
That, and you see this, with Christian here, he's sitting in the States, we do this globally.
That's right.
So we can, you can have exactly the same solution in the States, in Asia, in Europe, in Africa. So
absolutely. And we, Carrier has 55,000 employees. We operate in all 3 regions. We have manufacturing for each region. We have engineering design centers in each region. We have quadrupled our manufacturing footprint over the last few years. We've increased our lab commitment space. So it's been quite the journey for us, both collaborating with our customer, hyperscale and large colo and edge partners, but really also the industry leaders as well, as we continue to drive sustainable solutions for our customers today and the next gen.
Thank you very much, gentlemen. Thank you.
any questions?
So we have got time for a couple of questions, if anybody wants to do it. Anybody want? Oh.
There we go, good question.
Thank you. Great talk. Thank you very much, Michel. You totally got me at Q equal and CP delta T. I thought I was in the right room. So thank you very much for that. One question I have for you, actually. What is your biggest challenge right now on the engineering side? We obviously see a lot of the development that Christian showed and great product portfolio evolution. What is the thing that keeps you up at night, if I can ask?
I would say the size mainly, because I was on chiller development years, and I remember in '96 I was very proud. I developed the most compact unit in this time, and our objective was to put this chiller inside the container. Okay, so it was just standard container. We put chillers inside. And the capacity was 1.5 megawatts, so it was a kind of good enough. Today, we have to design, because as we said, 200 megawatts, 300 megawatts. Today, limiting factor is the physical size of the equipment which you can transport by land. So this is the design criteria. So you say, okay, if I could design air-cooled chiller with 5 megawatts, which I can transport, I would do this 5 megawatts. So people today say 3.2 megawatts, this is good. No, it's just, 3.2 is just, people are stretching design that this is about, 17 meters. You cannot have a larger truck in Europe. Maybe in States you have, bigger things. But this is, so the density of liquid-cooled data center translate on density of equipment which we are capable of doing, So this is probably the most challenging. Everything else, level of temperatures, dry cooler, adiabatic, etc. It's just, different operating condition. It's I'm not saying easy, but it's feasible. Yeah.
Absolutely.
Thank
Thanks for the
Brilliant.
question.
We're going to have to draw it to an end there.
Yeah.
D70, these gentlemen are going to be there. They said they're going to buy everyone a beer who comes and asks them a good question.
Good
So
questions only.
please go and see them, and hopefully we can reuse some of that energy asset, because, like you say, energy can't be destroyed, just transferred somewhere else, and hopefully keep our energy bills down and keep the data centers going. Thank you again. Please
you.
exit through that door.